Good morning to everybody. I'm Eros Spazero from the Polytechnic of Turin, Italy. And today's lecture comes from my lecture on this summer biomedical school. It was a 4-hour lesson, but don't worry, today only 20 minutes will be enough to see together some items that can be useful for this study. Let me share the screen. The title is Medicine 4.0, when the new technologies work with artificial intelligence. Medicine 4.0, because today Industry 4.0, everything is 4.0. And artificial intelligence, the same. Today, everything is artificial intelligence. So how can we put together medicine, artificial intelligence, and the IEEE Instrumentation and Measurement Society? So today we will see what is a telemedicine, what is electronic health, medicine 4.0. We will see together some new wearable devices and their interaction with artificial intelligence and the interaction between all these things with the Instrumentation and Measurement Society. Telemedicine comes from the requirement to have the possibility to have a contact with a lot of people. The baby boomers in the 50s mean today that a lot of people aged more than 60 years, I am an example, need to have care because after all these years, our body is not so efficient. People's life expectancy increased. 100 years ago, our life expectancy was 21 years less. And today, so we have a lot of elder people with not so good bodies. We need more doctors. But unfortunately, modern society has less money for health. And this means that we don't have so many medical doctors. So the problem is that we have more patients, less doctors, less money. And how can we solve this problem? An idea is to delocalize the services, to allow people to have not every service, but some important services at home with no caregiver, but without lose the quality of medicine. Today, these three concepts are more important because COVID-19 does not allow any physical contact between people. So how can a doctor visit a patient? Electronic health, electronics. My laboratory is an electronic laboratory, and we develop new devices using a new circuit. For example, 6 years ago, we developed an electrocardiogram ACZ watch, I will show you, and can give precise indication for atrial fibrillation, can communicate with a remote cardiologist, so can be useful to check some disease, not every disease, some disease. Photoplethysmography again can be very important to have information about your respiratory system. Again, today with COVID, this is a very important parameter, but also image processing. We use the smartphones with their electronic cameras to check a lot of problems, send information, images to remote doctors, and make a diagnosis using artificial intelligence. This is the idea, okay? And we have to remember that traditional systems, we already have ECGs, sphygmomanometers, and so on. But elder people are not so happy to make a setup and to calibrate the system. They must be very simple and low cost, of course. Otherwise, only rich people can have these tools. Okay, this is just to show you our ECG watch. Unfortunately, is in Italian, but I will comment in English. You see, this red is our first ECG watch in 2015, and this is a very low-cost smartphone, an old Samsung. Okay, the cost of this ECG watch is very low, 30 euros, and the smartwatch is 50 euros. So anybody is able to use it. You see that the person is pushing one finger only, nothing else. And after 10 seconds on the smartphone, you have your electrocardiogram and your heartbeat, and maybe an alarm if you have atrial fibrillation. But if you are not an expert, the smartphone in automatic way send the electrocardiogram data to a remote cardiologist together the GPS position of yourself. So you can be easily found if you have problems. The remote cardiologist has a personal computer with a special software able to make measurements, to check times, and to put filters, and so on. A lot of important information. You can find our information in this paper published in Sensor. Okay, electrocardiograms, you see, very easy. One finger, 10 seconds. But today you have to call a doctor, and when in Italy, for example, maybe you have to wait a lot of days or a lot of weeks. You have to wait your turn, go to the doctor's studio. If a doctor's studio is 100 kilometers from your home, you have to undress, attach the electrodes, wait the report, go back home. And if you have an urgency, oh, very bad. By the way, we don't want to replace electrocardiogram and cardiologist. These are absolutely necessary. But for some cardiological disease, just a simple watch is able to detect, for example, atrial fibrillation. I am a patient, I have big problems with atrial fibrillation, and I detected my atrial fibrillation using my ECG watch. When my ECG watch told me, oh, you have atrial fibrillation, very high heartbeat, I called my cardiologist and I had a traditional ECG. But if I don't have any warning, no problem, I don't go to my cardiologist. So the idea is to have new devices, okay? New devices means one-touch devices, no setup, no calibration, nothing difficult. Also, sphygmomanometer can have a problem. I tried them, and if you are not careful, you can have different and wrong measurement of your pressure. You need a caregiver, yes, but a caregiver has a cost, and in the COVID pandemic situation, it's not so easy. So we need a new concept for new medical devices. When I speak about Industry 4.0, everybody knows that every 100 years, industry has a new step, Industry 1, Industry 2, steam power, electrical energy, computer networks, and so on. And medicine? Medicine is lower. So I think that we can state that medicine 1.0 was when Watson and Crick described the DNA structure. Medicine 2 is the sequencing of the human genome when we were able to find the origins of disease. Medicine 3, when biologists and engineers work together. And medicine 4, today, when we are able to have digital signals. So the digitalization of the process of analog signals. This is very interesting, but here the instrumentation and measurement society can give a significant contribution. When I speak of telemedicine and have a look at the internet, today I only find a friend phone. Okay? A remote patient can speak using a smartphone or a tablet with a remote physician. Good. This is a good approach because he can speak, but the remote physicians has no data, only opinions, only words, so no signals about vital signs of the remote patient. This should be the right way. New instruments able to check vital signals on the patient in a remote way. They must be easy to use, low cost, fast. They can communicate to a smartphone using Bluetooth, and the smartphone is able to communicate to remote physicians, giving also the position of the patient, and maybe can give a warning for serious disease. Okay, this is the idea, to have these simple instruments, and all these pictures are describing our instruments today, and a typical app for a smartphone that we use. So to do all this, we need the new electronic devices and artificial intelligence to make intelligent diagnosis. Okay, artificial intelligence. Artificial intelligence is a difficult word because today everything is artificial intelligence, but this is not precise because artificial intelligence was born in the 50s when a group of scientists using new languages, Prolog, Lisp, claimed to be able to replace human brain. A lot of money, a lot of research, but after 10 years, no results. And so this was the end of real artificial intelligence. This was a top-down approach because they didn't know nothing about inside the brain. Another approach, bottom-up, comes from McCulloch and Pitts, who created a mathematical model of a human neuron and a human synapses. And they built a model which was called the perceptron. This model was based on the simple neuron and the simple synapses. More precise neuron and the synapses models were developed in the following years, but no problem. The simple perceptron is enough. Again, also this approach has a good success, but when they thought to use this approach to replace human brain has 10 to 11 neurons and 10 to 13 synapses. It's impossible today with today's technologies. It's also impossible to simulate with this approach. But a new approach today is available, deep neural networks. They are an evolution of multi-layer perceptron that is an evolution of the old perceptron. They were not able to work up to a few years ago because we didn't have a powerful computing system. But today we have. Today we have cloud computing, we have big computers. So natural language processing, for example, think to Alexa, is using cloud computing or facial recognition, three-dimensional structure of a protein. A lot of applications, not an artificial brain, a lot of application. This is the key to solve a complex problem. But in this approach, we use algorithms based on data. No mathematical models. Deep neural networks are big networks using a powerful computing system. No mathematical models, but a lot of data. If you don't have data, this can be a severe problem. So I can show you a lot of examples, but I just want to show you the blood pressure where we are trying to evaluate systolic and diastolic pressure of our body. Up to date, the gold standard is invasive intra-arterial catheter, which is able to monitor blood pressure. It's really invasive. So only intensive care unit use this approach in critical cases, not really possible. Sphygmomanometer, a physician is able to use it on your arm, inflate cuff around your arm, and so on. You need a caregiver, and today with COVID, this is not possible. No problem. We also have a sphygmomanometer to do self-measuring blood pressure. Unfortunately, I tried a lot of these instruments, they are not so reliable because if you are not very efficient in put your cuff or fasten your cuff, the error is really big. But we are engineers. I'm an engineer. Can we use a mathematical model? For example, you can find a Young model where you measure the pulse wave velocity, that is the speed of the blood pressure pulse traveling along the circulatory system. These are the parameters: thickness of vessel, blood density, vessel diameter, not so easy to have. I don't know why, for example. Another model, Funk's model, is measuring the pulse transit time, that is the time taken by the pressure waveform to propagate through the blood vessel. Again, a lot of parameters and not so easy to estimate. So you have poor precision using this model. Can we replace mathematical models with artificial intelligence? Oh, yes. We used a database coming from the United States where you have thousands and thousands of measurements with ECG, photoplethysmography, and also invasive arterial blood pressure. So we We have a golden standard and the tools that we are using with our electronic devices. This is diastolic blood pressure measured and simulated by our deep neural network, and the same for systolic. To be more precise, this is the sphygmomanometer used by a caregiver. And as I told you, this instrument is not perfect. So the error that you have is 4.1 or 4.7. With neural network, we obtained 3.2, 3.6. So it means that just using electrocardiogram and photoplethysmography, we were able, not using nothing, I mean just with one finger device, to have good values, okay? And this is, I think, a new wave to investigate. Maybe somebody is thinking, but what is the precision accuracy of these sensors? This is a very difficult question. I mean that we measure data that are analog data, are converted to digital, and we have an analog neural network to perform a digital work. Artificial neural networks or deep neural networks are black boxes. We are not able to understand numbers inside. How reliable can be considered? And moreover, one of the strongest points of the neural networks is their capability to make generalization. But generalization is not a good issue to evaluate the right number, the right value of blood pressure. So this is a strong point to be evaluated, and we are working on it. Okay, I've just finished, and in only 20 minutes, I had the possibility to say that telemedicine can use artificial intelligence to measure medical data in a different way. Maybe this approach can overcome weak points of the traditional measure, but the results must be validated. Accuracy and precision must be validated. So we have a work for IEEE Instrumentation and Measurement Society. If anybody is interested in these topics, please contact me. I will be happy to speak with you. Okay? Thank you very much. And if you have any question, can write me an email. Bye.